Hello everyone. In the previous class, we discussed about the voltage to frequency converter using the IC9400. The same IC can be used for the frequency to voltage conversions, which will be discussed today. So an IC 9400 based frequency to voltage converter, which generates an output voltage which is linearly proportional to the input frequency. So there is a linearity factor. And the main features of a frequency to voltage converter using the IC9400 are which can be used either the DC voltage or AC voltage to up to the 100 kilohertz. It has got a very high input impedance. So the comparators used here has a hysteresis values of plus or minus 200 millivolt. So the input which we are giving here should have a value which is higher than plus 200 millivolt or minus 200 millivolt. So in these conversions where the frequency is inputted into the positive input of the comparator. So here you can see that this is the frequency input and the output will be voltage which will be collected across the C integrated. So that will show the full diagram in the next slide. But whatever frequency which we are giving here should be bipolar. That means it should have a positive and negative peaks. So if you have only the positive peaks, then we cannot convert this frequency to voltage. So here you can see a unipolar signal. So this kind of signal is called unipolar, which has only got the positive height. There is no negative signal. There is no negative peak here. So we have to convert this unipolar signal into bipolar. So for that purpose, if the input is a unipolar, then we have to use a voltage divider like this. So this is the input which has got a 0 to plus 5 volt peak here. So this will be converted into, using this voltage divider network, this will be converted into a bipolar signal with plus 2.5 volt and minus 2.5 volt. So it has got a positive and negative peaks. So now we can convert this signal into voltage. So the height, the amplitude of the signal is not changed. Only thing is it has to have the positive and negative peak. So here is the block diagram for the frequency to voltage converter using the IC9400. Here there is the comparator. An op amp is used as the comparator and the frequency input is given to the non-inverting terminal and the inverting terminal is grounded. So if the frequency given here is a positive signal, then the output of comparator will be positive since it is given to the non-inverting terminal and this terminal is grounded. So the output it will be positive and it is plus 1 and this is given to a 3 microsecond delay network. As you know, this is an inverter, so the output will be 0. So now the output of the 3 microsecond delay network is 0, which is given to the input of the divided by 2 network. As we discussed in the last class, inside the divided by 2 network there is an inverter, so that the output will be 1. So that is the output which is given to the input to the base of this transistor Q2. So now the transistor is on, so that the output F0 by 2 here should be 0 because now the transistor is on, so that it can flow current through this. The collector current can flow towards emitter. At the same time, the input which is given to the charge discharge control unit, that is from the output of 3 microsecond delay, so that is 0. So that 0 is given to this control unit. Now that 0 input to this unit will disable this one, so that the capacitor, the C reference capacitor is not connected with the reference voltage now. So it is disabled. So at this time the input to the Q1 is also low, so that means the output here should be maximum, that is the plus 5 volt that will be appear here. So in the next steps, let us consider that the input frequency given here is a negative signal, so that the output of the comparator will be low. So this output will be low, so that means the output of 3 microsecond delay will be higher. So this one higher means this is the input to the divided by 2 network, so that this will be 0. So that makes this transistor off, so that the output here should be high. So at the same time, since this is 1 here, the Q1, the input to the Q1, the output of this transistor Q1 should be low. Now the input to the charge discharge control unit is 1, so that will enable this control unit, so that now the reference capacitor C reference will be directly connected with the V reference, so that it starts charging. That means when this charge discharge control unit is enabled, this one, so this capacitor C reference, this one is directly connected here, and it's charging through the V reference here. At the same time, this C integrated also will be connected. C int also will be connected using the same charge. So the output which will be taken across the C integrated, so now it shows is charges, and it shows the corresponding voltage. So that means whenever this charge discharge control unit is enabled, this C reference will be directly connected with the V reference, and it start charging, and the same charge, this also will be charged. So at the same time, the C integrator also will be charged up to its maximum value, and we can measure the voltage here, which is taken as the output voltage. So we know that the input frequency given here is a bipolar signal. So at a later time, this can become positive. So now, since it is positive, means this output of comparator is high, so that makes the output of 3 microsecond delay network low. So that makes this charge discharge control unit disabled. So that means now it is not connected. So now this is connected here. So now the C integrated, which is charged to a maximum voltage of VO, can discharge. The only discharge path it has is the through the R integrated, that is a 1 mega ohm resistor, which is very high resistance value. So it cannot discharge. There is no discharge path for this. There is now whatever voltage stored here will be remains the same. So now we have converted the frequency value here to corresponding voltage here. So this slide shows the waveforms. So this is our bipolar input waveform, which is having both negative and positive signals. And here you see the output of Q1 and Q2 transistor. So finally, we are converting this input frequency into output voltage, and the output voltage is related to the input frequency by these transfer equations, that is V out is equal to V reference into C reference into R int into F int. So of course the output voltage will be having some unwanted signals, which is called the ripples, and the amount of ripples which are present in V out is inversely proportional to the values of C integrator and also the input frequencies. So we can of course increase the value of C integrated so that we can reduce the ripples. So that is one way. So there is another way is the most common way is using a common mode configuration op amp. So this is the ripple eliminator circuit. So this is the input to the signal is the VC integrated, that is the voltage across the integrated capacitor. That is the signal, the voltage which we want, and some unwanted ripple voltage V ripple. So when we use in these configurations, we have, this is in the common mode configuration, so that these unwanted signals will be eliminated, and in the output we will only have the voltage across the C integrated, that is the VC integrated. So to conclude, using the 9400 IC, we can get an output voltage V out, which is proportional to the input frequencies. So thus we are converting a frequency signal frequency into corresponding output voltage, which are proportional to each other. So that's all about the frequency to voltage converter.